so let us continue to talk about the fundamental key system. Before we have the fundamental key system, we need to have the concept microprocess. Therefore, we have the definition microprocess here. Alright, so for all of you can look at this microprocess and checking the definition. And then it has the standing page the standing page of the group to each group. Okay, so microprocess actually depends on the current state rather than the previous states. So, for example, here we have all of these, and then we can change based on the current state. Only the present state. Alright, so then we can have the state transition diagram like this. So, we want to apply microprocess later to help us to analyze the system. So this is the microprocess. And one specific process actually is a microprocess, but we call it birth and death process. So that is a special type of microprocess. And why we want to use it? If we have some size, specifically population. Alright, for example, number of jobs in queue. Currently, we want to consider this number of jobs in queue to have the analysis. Right? And why we have both? For example, or maybe later we have the standard transition diagram. We can let it know. Oh, we have one direction. The direction brings the birth, and another direction brings death. In that sense, we can increase so that we have the direction of birth, and we want to decrease, and so that we have the direction of death. And we can pass on the two directions so that we have the microprocess, and this kind of microprocess we call birth-death process. Well, in fact, we have the special microprocess. But right now, microprocess, we gotta have the rate. So we have the direction to represent birth. And here the state means the population size. Alright, and this direction death. And we have the corresponding state. So from 0, then we have lambda sub 0, and 1, then we have lambda sub 1. And then it's up, we have the corresponding index 1 because of the current state, population size. And this is the state transition diagram of a birth-death process. But we gotta know, oh, okay, it's continuous birth-death process. Continuous means we have the index continuous time, so that we call it the continuous birth-death process. Should we include continuous here? Actually, later we will have if we just try to have a different way to share. Perhaps we don't call this continuous birth-death process. So currently, let me simply call we have the birth-death process. And this birth-death process, we can have the state transition diagram. Then we will pass out the state transition diagram to help us have the performance measures. To have that one, we will pass out that. So right now we have Markov chain. Markov process. Maybe we should call chain. In fact, right now, because of the process, so it should be continuous. And if it is discrete time one, we should call Markov chain. In fact, sometimes it should be Markov chain, so I already have a Markov chain as well to both things. And then right now we want to have MM1. So we just follow the track, and so that we will formally apply some technique to have a performance measure for the process MM1. Because we want to then have the traffic theory and then have a system. And this system serving as an example. Well, so MM1, based on the previous can-down notation. So M, we should have the exponential interval time, and service time follows the exponential time as well. So one, we have a single server. Even we don't have the fourth and fifth positions. Actually, we have MM1 infinity. So we have the size, the buffer size should be infinite size. Alright. For this kind of system, actually we allow the customer to arrive. And it will be served only when the server is free or is idle. Otherwise, the customer needs to line up in the queue. So it will be queued. And currently we don't have the specific description about the service discipline. So we have the simple one, first in, first out. Just come and work in order. So this is the first in, first out. And we have the actual assumption. We have an independent, identically distributed. So IID. Independent, identically distributed random variable for interval times. Because of the songs, of course, it should be IID. But right now we enforce the interval times are IID so that we have the song process. And likewise for service time, they follow IID random variables as well. Right, so here we try to emphasize we have the possible feature of all the system of MM1. So this patch actually, that all of you to understand we have a system. This system based on the can domination. We have MM1. And how to have the real operation, this one. We have a queue, and we have a server, a single server. We have a customer. And once finished service, then depart. Alright, so this is the really, maybe not massive, but at least really simple queuing system. So we never have this one because we still can have the extended one, but we started from this one, MM1. And likewise, we emphasize MM1 skip this. So this one skip, but we emphasize explicitly. Don't forget we have the size. The size is infinite size. So infinite size here. Well, maybe something wrong. So previously we should have the rate change, but we have this rate change here. So something wrong, but let me continue. for this M1, so currently actually we pass on MM1. And we start from both test process into the curve one. Both test process we mentioned. Oh, we should have the rate depends on this. Depends on this, but look at this. No. So this is 0, 2. The others equal to lambda. Likewise, mu 0. It should be mu 1. So the others equal to mu. Therefore, M1 is a special case of a both test process. So we have the special case already. And for the special case, we will have the variation for the performance measure. Well, about this, maybe let me ask you this first. About the current system M1, and later we will have the analysis for this M1. About the M1 here, any questions? In fact, I don't have the poll, I'll ask you directly, so any questions? If yes, raise your hand and let me know. No, right? So, let me go to the next one. It's an activity. Attendance checking, something wrong, so let me refresh it. Okay, so this is a panel check-in today, and you can scan the QR code and join. And sometimes something wrong, so I need to refresh it so that we can have this. Go and check it. So you can continue. So anyone else have to fill in this form? Consent to recode. Finish right. Okay. You finish it? And how about Jen? About the form here? Okay. No, I mean this form. You finish it? Consent to recode. So you You can check it inside for me. And how are you? Got it? And finish it. Finish it? Okay, thank you. Alright, so if that's okay, let me go to the next one. Before I go to the next one, maybe, sorry, I forgot to activate these. If you need to scan these, you can scan the QR code here. Alright, so let me move on to the next one. If I want to have the equilibrium state equation based on the previous step, actually the state transition diagram. So we will have the equilibrium equations, and so we have the form, this one. Oh, we want to have a probability. Here is probability. Set probability having I customer in the system, and we have the equilibrium equation. Alright, now I want to know how to have the equilibrium equation, and so that we can have the formula here. Once we have the formula, then we can derive the results. So look at this. We have a 0, lambda, 1. Maybe to I use I. And we have I and 2. We have a lambda, and we have a mean. And we have as I use I minus 1. Alright, so we should have the state transition diagram like this, right? And so then how to have the balance equation? Actually for the current result based on this, a circle. Approach 1 use a circle. With a circle, then how to have the balance equation, or maybe the equilibrium equation. If I want to check, rate. Actually, these are rate, and these are rate. And I don't mention the rate. This is arrival rate. And this is the departure rate or service rate. Right? Arrival, so we have a force to come to the system. So this is arrival rate. And another direction, we have the service rate and departure rate. Service once finished, and then the customer can leave, and can leave, then it will depart. So it is called the departure rate. Well, so if we have a circle and the rate, right now we have the two rates, arrival rate and departure rate. But for a circle, we can have a rate out and a rate in. So that balance, we should have a zero net rate, right? Zero net rate, it says we should have the rate out equal to the rate in. Alright, so rate out equal to rate in, so we have this. Sorry, maybe then you enjoy it. So I simply emphasize I minus 1 and I we have this. Rate out. So first of all, rate out. Is equal to this. E of I over B multiply lambda and multiply mu. E of I is rate out. And how about rate in? We have this. And set the two rates to be equal, and so that we have the balance equation, right? So currently, is it okay? If it is okay, look at this. The second one. Right? So here is rate out, and the right hand side is rate in. Am I right? But we have a special case, the first one. So currently we can have this. Why we have for the first one? Why we have for the first one? If we have this only, okay. So anything wrong? So how to have the first one? I check the second one. I want now another check the first one. The first one is 0 and 1. So we have a lambda and we have mu. And likewise we can have a circle. The circle only focus on 0. 0 so we have a rate out. It's this. And rate in, we have this. 1, so it's mu. So that we have this. Right? And you can check this is the first equation. Alright, that's on the first equation and second equation. They are balance or co-equilibrium state equation. Pass on the two equations, then we can derive this one. Alright, so we already have for this one. It's the first one to have for the result. How to solve it? Recursive formula. So you can pass on some concept from discrete mathematics and recursive formula to have the result. You can try this concept, how to solve it. However, let me have a quick way to have the result. Same. We have a 0, 1, maybe to I minus 1, then to I plus 1. I know the other, simply have these. Previously we use a circle, but second way we use a line. Or maybe it's a plane. Alright, so how to have that? We have these. A cut is a line. So which one we use it? Pass this one. Or maybe this one. Okay, let me try this one, the second one. So if this one we have a line, so that line will have to rate to the right hand side and rate to the left hand side. So here, rate this side, so it's equal to this. And how about rate to this side? If we consider they should be equal, so we have this one. And finally, the balance equation should be this. Alright. Actually, maybe it's my fault we should choose the first one. The first one will have the generalized one. But it doesn't matter. We have the general equation based on the curve where it's a cut. If we have a line, finally I should ask, the curve one can be generalized through the other cuts? Yes. You just try to change the index. And so therefore, for the curve system, we should have this. We should have this. Oh, okay. Right now we have a lambda pi and mu pi plus 1. Actually, we focus on this. Pi plus 1 larger is equal to lambda over mu and pi. Alright. And if not, we can have the others. Pi equal to this. Actually, we can start from this. If we start from this, let us have this one. Using rho to denote this. Oh, okay, I start from this. It's rho, but this one equal to it's rho again, it's I minus 2. So we have rho square pi minus 2. And you can continue. 2. So it should be I minus, So it should be I minus I, so we have rho I p of 0. Is it true? So based on the curve way, the second way we have the relationship, and this relationship actually is 1. Am I right? Therefore, you can pass on the curve equation using recursive formula so that you can have the solution. Or maybe you can pass on the quick way. We use a line so that our plane, so that we can have the relationship P of I equal to rho raised power to I and multiply P of 0. Alright, so either way we can have the solution, but we pass on the solution to continue to have our performance measure. And before we go, so we have the definition. I probably have a rho already. So we have a rho defined by lambda over mu. This one is called traffic intensity. Why traffic intensity? Intensity here we use mu to serve as the normalization factor. Oh, we have the arrival rate. Arrival rate says, oh, we can have 10 cars per second to arrive the system, but we serve them using 12. So this is the force to arrive or to depart. And the through normalization is 1, lambda over mu. And so that we expect this one should be lower than 1. Why lower than 1? If we have 12 customers per second come to the system and you just have the capability 10, you can serve 10 customers per second. So using 1 second to think about this, I just can serve 10, but how about the remaining 2 customers? The queue there, right? And 1 second you can queue 2 customers, and next second queue 2 again. So finally, you have something like task you cannot finish. And so, is it stable? No. It doesn't mean not stable, but well accumulated the customer, and you cannot serve them. And so that you always can queue. So it's a problem. Because of that problem, so we have the condition. The necessary condition. This one, steady state. Why steady state? If we queue two customers in the queue and we all the time two and do the other so that it won't be a stable one. Actually, we have the explosion problem, right? Explosion problems, of course, we cannot have the steady state. Alright, so of course we can have this. I don't have the notation in advance, but actually the notation it is called traffic intensity. And the traffic intensity it should be this one. And in fact, we have the traffic intensity, and traffic intensity says P of 0. Sorry, not P of 0. We want to have a P of 0 of course saying this. And what's the relationship? P of 0 and rho. Here, we get it out from the first result. If we have this, actually later we will let it know, oh, P of 0, we should have this. It should be this. Why? If we use this one to have the interpretation. Rho means I should serve. So 1 minus rho says, oh, okay, this is a function, it won't be necessary for the server to serve the customer. So 1 minus rho should be this one. If 1 minus rho, no customer to come, so it should be P of 0, something like that. So is it true? Later we can derive that. But we mentioned rho is the traffic intensity. And let us try, oh, okay. We use a different way. Rho should be 1 minus P of 0. Right? So maybe if either way, you use this, P of 0 possibly should be, possibly later we can derive it. Oh, rho equal to 1 minus P of 0. Either way you think it's comfortable to accept, that's okay. But right now maybe you think, oh, okay, I don't feel comfortable to accept this one. So later we use a way to derive it. So that we have the rigorous way to have it. But we mentioned, sometimes we should have that, and so that we have some result. But right now, it should be rho, but something wrong, so it's R here. Alright, so finally we have the form, but let me show you later. Actually, first equation, P of I, or maybe previous equation, rho, or P of 0, or later we have the performance metric. We want to derive this. Add number of customers in the system. We have the formula, and the average time of a customer. We have the form here, and how to derive the result. So in fact, let me have the first equation. And actually, it's a 0 equation, and the second equation and third equation. So how to derive it? You should understand we have this. Right? But we still have another equation. Before I continue, this is the required equation. Any other equation or condition should be added to the third equation. Anyone can come up with the missing equation? Perhaps no. The answer is this one. So actually we have the two equations. This is a condition. Actually it's a condition. Why this kind of a condition? Why this kind of a condition? Why this kind of condition? Step 0, step 1, step 2 to the others. Actually, we can collect all the probability because of all the probability. So that says based on total probability. About the total probability, condition, so that's our condition to substitute this one into the condition. So we will have this. Because of 1, so we have this. And we have the form. Right? So the current series actually we have for the solution, it should be this. 1 minus rho, and the first term should be 1. Am I right? Fine. Here we have this. It's 1 plus rho square plus the others. Right? It is a geometric series. So geometric series, this is the form. 1 minus this and the first term. So first term here. And this is the ratio. Rho over 1 is rho. And so then we have the result. Once we have the result, then it says, oh, equal. Because of equality here. So P of, sorry, not this one. Because of equal to 1, so 1, this one. So we have the result. Okay, finally we have P of 0 equal to 1 minus rho. So this is zeroth equation, right? Once we have a zeroth equation, then substitute this one into the form here. Okay, it's 1. We just need to have a rho. So we have a rho equal to 1 minus P of 0. Oh, sorry, wait a moment. Not this one. So replace this. So we have the first equation. The first equation says P of I equal to rho I is. So that should the first equation equal to this. Yes, this one. Rho I and P of 0. P of 0 equal to 1 minus rho. So right now we reach the first equation. From zeroth equation to the first equation. Up to now. Is it okay? And we have both of them here. We have a balance equation, but we have a condition, missing condition. Put them together, we can have P of 0. P of 0 equal to this 1 minus rho. Once we have P of 0, substitute P of 0 by 1 minus rho. So of course we have the first equation. P of I equal to rho raised power to I multiplied 1 minus rho, right? And so we can have the first equation here. Once we have the first equation, maybe you have equation how to